In this example, 3 fair coins are tossed. For part A, we need to write down all the possible outcomes when the 3 coins are tossed. So in this scenario, because we're dealing with a low amount, we can create a scenario that can show how we can get the possibilities of getting heads or tails for the 3 coins. So this is how it would look like. So for the first scenario, we have 3 heads. Second scenario, the number of possibilities are 8 here. So 2 heads, 1 tail, 2 heads, 1 tail, 1 head, 2 tails. Again, these are representing the first, the second, and the third coins. So we're looking at in the scenario 8 possibilities. So this is what we will need to make note of. Now for part B, a random variable x is defined as the number of heads when the 3 coins are tossed. We need to write the probability distribution of x as shown on the right hand side with more clarity on how we can populate that, but we'll explain this example in more detail. So for the first part, we need to populate it through a table. Now we'll populate the table through looking at the scenarios here. So we're told that we have number of heads. We're given the random variable is 3, so we're looking at 0, 1, 2, and 3. So how do we get the values of probabilities for the 0, 1, and 2 or 3? So we know that the 3 coins having tail, that gives us the 0, and that will be equivalent because it's out of 8 possibilities, so we can write it as 1 over 8. So this is why we have the 1 over 8. And for 1 head, we have, this is the 1, and this is the 1, and also another one here. So we have 3 possibilities where we can have in terms of 1 head. So this is 1 over 8, 1 over 8, and also another 1 over 8. So these 3 will be added, so that will give us 3 over 8 for the 1. Now for 2 heads, we have here, that's 1, 2, and 3. So similar scenario, so we would add here it's another 1 over 8, another 1 over 8, and another 1 over 8. So that will give us another 3 over 8 for the table. And for the third, having 3 heads is only 1 scenario. So this is 3, and this is 1 over 8. So this is how we populated this table to show the number of heads and how we can get the probabilities to using to achieve these or the possibilities of getting a head or 1 or 2 or 3. Now in terms of populating through probability mass function, we will also see the scenarios what we have. So for the achieving 1 over 8, there is 2 possibilities, either 0 or 3. That this is the possibilities that we're looking at, as there is 2 scenarios. And the 3 over 8, we have 2 scenarios, which is either 1 head or 2 head, and achieving 0, which is not possible in this scenario because we will have to toss. So that's why we suggested it would be otherwise. And this is our breakdown of the solution and how we can look at the variety of looking at it through obtaining it through a table, or looking at the scenario where we need to look at the probability mass function. And this will be our answer for this question. In this example, a biased 4-sided dice with faces numbered 1, 2, 3, 4 is rolled. The number on the bottom most face is modeled as a random variable x capital, given that p to the x capital equal x equal k over x. Now we are asked to find the value of k. So in this scenario, we used so the probability distribution will be looking at the values on the faces, which is 1, 2, 3, 4, and looking at the value of k, we would have either k, we sub these values into the k, so we have k over 1, which is k, k over 2, and k over 3, and k over 4. Now what we would look at in this scenario, we will equate all these values to 1. So we would have k over 1 plus k over 2 plus k over 3 plus k over 4 equal 1. Now the next step will be taking the k as a common factor and adding the fractions to each other. So that would give us, and also simplifying the expression, so that will give us the denominator a 12, and then we would have 12 plus 6 plus 4 plus 3 on the left hand side. On the right hand side we would have 1, and we will try to simplify for k, that would give us k to be equal to 12 over 25, and this will be our value for k. Now for part B, given the probability distribution of x capital in a table form, so for us to create a table form, we will start with looking at the possibilities that we will have in terms of the faces, which is 1, 2, 3, and 4, and we know the value of k is 12 over 5, so k over 2, that would give us 6 over 25, k over 3, that would give us 4 over 25, and k over 4, that would give us 3 over 25. Now for part C, we need to find the probability that x capital is smaller than 2, and also when 1 is bigger than x and also bigger than 4, and also we need to look at the probability when it is smaller than 4. So we will start by looking at when probability is smaller than 2, so it will be the same as getting 3 or 4. I mean bigger than, so we're looking at the probability of x being bigger than 2. So it will be the same as getting 3 or 4. So in this scenario, we're looking at taking the k factors. So we'll have 4 over 25 plus 3 over 25. So that would give us, in this scenario, 7 over 25. Now, if we are looking at the probability when being smaller than x and also smaller than 4, so that will be looking at the 2 and the third random variables. So in this scenario, we'll be having the probability it will be 6 over 25 plus 4 over 25, which will give us 10 over 25, which can be simplified to 2 over 5. And this will be our answer for part II. For part III, where x is bigger than 4, there are no elements in that sample. So we are mainly looking at bigger bigger than 2, and also we looked at also smaller than 4, and in this scenario we're looking at bigger than 4, and there are no elements in that sample. So this will be our answer in this scenario, and we will also need to explain that space that satisfies the probability of x being bigger than 4, so that will be equivalent to 0. And this is to summarize our answers for part C, looking at I, II, and III. In this example, the spinner is spun until it lands on red or has been spun 4 times in total. Find the probability distribution of the random variable s, the number of times the spinner is spun. So first, we're told that the spinner is spun and needs to land. So in this scenario, we'll look at s being 1. So in this scenario, when s is 1, the probability that the spinner lands on red first time. So we will look at the possibility, because we will be an outcome of 5 out of, as we can see, that it is broken into 5 sections. So that will mean, because we have 2 sections are red, so that will be 2 out of 5 possibilities in this scenario. Now, in terms of if the spinner lands on red on the second spin, it must land on the blue on the first spin. So what we'll be looking at in this scenario, when for the second spin, it will be 3 over 5, because there was 3 blues out of 5 and there was 2 reds out of 5. They'll be multiplied by each other, so the possibility of landing, it will be 6 out of 25, and this will be our explanation in this scenario. So we'll have the probability of blue then red, and that will be the probability of blue multiplied by the probability of red, and that will give us 6 over 25. Now likewise, for landing on the red on the third spin, then we would look at the similar possibilities. When we have, for the third spin, we would have 3 over 5 multiplied by 3 over 5 multiplied by 2 over 5, because we can see in this scenario that there is 3 possibilities for blue, so we'll consider that into the account. So we'll multiply all 3, that will give us 18 over 125. Now in terms of the experiment, when the experiment stops after 4 spins, so we will need to look into take into account out of 1. So 1 represents the whole complete value that when no spins are achieved, when looking at the full scenario, and looking at the scenarios when there is 1 spin, 2 spins, and 3 spins, being all all added to each other and taken away from 1. So that would give us 27 over 125 in terms of representation of the fourth after the fourth spin. Now, in terms of also representing how would these number of spins aligns with the probabilities for first, second, and third and fourth, we can create a table which shows the first and second and third. So for the first, we achieved 2 over 5. For the second was 6 over 25. For the third is 18 over 125, and for the fourth is 27 over 125. It shows the possibilities of achieving in terms of red or within the probabilities that we have here. So this will be our answer in terms of explaining how we can achieve the variety of probabilities for the first, second, third and fourth spins. In this example, write down whether or not each of the following is a discrete random variable. Give a reason for your answer. For part A, we need the height in x capital centimeters of a seedling chosen randomly from a group of plants. So our answer in this scenario will be this is not a discrete random variable since height is a continuous quantity. For part B, the number of times R capital a 6 is rolled when a fair dice is rolled 100 times. So in this scenario, this is a discrete random variable since it is it takes a whole number values at random. For part C, the number of days W capital in a given week. So in this scenario, we will need to take into account that this is not a discrete random variable since the number of days in a given week is always 7. The result is predetermined and so not random. And on the right hand side, it gives you the definitions for the discrete and random and more insight in terms of how you can answer these types of scenarios. And this will be our answer for this question. In this example, a fair dice is thrown 4 times and the number of times it falls with a 6 on the top y is noted. Now write down the sample space of y. So in this scenario, we have 4 times. We need to find it is thrown 4 times, so we need to consider that there is the 4 possibilities. So that's why it will be starting from 0, and then there is the 1, the second throw, the third throw and the fourth throw. So this is what we're looking at in terms of the possibility in terms of achieving 6 and being noted, and this will be our answer for this question. In this example, a bag contains 2 discs with the number 2 on them and 2 discs with the number 3 on them. A disc is drawn at random from the bag and the number noted. The disc is returned to the bag. The second disc is then drawn. A second disc is then drawn from the bag and the number is noted. Now, for part A, we need to write down all possible outcomes for this experiment. So in this scenario, because we have either number 2 or number 3, but we have 2 of each, so we're looking at the possibilities shown. So either both of them will be 2, or both 1, 2 is 1, 3, or 1 and 3 or 1 and 2, or both of them are 3. So these are the possibilities we are looking at here. So in this scenario, we're looking at 4 possibilities when they're now. The discrete random variable x capital is defined as the sum of the 2 numbers. Well, we need to write down the probability distribution of x capital as either in the form of a table as part I or a part I, a probability mass function, which is more highlighted on the right hand side. Now, to start with the table, we can see we can have either probability to get 4, 5 or 6. Now the 4 and 5 or 6 is the addition of the probabilities shown, so we can have either 4, these 2 is 5, and here is 6. So this is the probabilities that we took into account. So if we add, because we have out of 4 possibilities, so this is where we have here is to get 6 is 1 out of 4, to get 5 is a half, because 2 quarters, so you can add a quarter plus a quarter, and to have also 2 over 2, that's another quarter here. So this is how we populated our table for this part. For part I, a probability of mass function. So we would look at first when it is a quarter. So this is based on the table scenario here. It's either when it's 4 or when it's 6, the addition of the values, or we can get a half when x is 5. 0, we say it's otherwise. So scenario we are not aware of. So this is our explanations for this question and how to answer parts of A and B, including I and double I.